Too late. Okay. Right, you ready? But I guess handle mic.
Testing, 1, 2, 3.
We're the first group to have joined.
Testing, 1, 2, 3.
There's Sebastian, and he is in Kerala, India, one of the participants, and that's us.
Sure, bit more volume, by chance.
Okay, I can see our guests are arriving already. Hopefully you guys are going to be typing in the text part. You're not going to have the volume tab.
Okay. So welcome. Every special guest from NASA. We have Dr. Stofan, and she is the chief NASA scientist. Not a NASA scientist, NASA scientist, which means also has NASA astronaut Cady Coleman, and he has made.
I go to chat. Type in difficulty here, chopping in and out. Just the use APAR.
A consul general of the United States Embassy instrumental in bringing our specialists to the round of applause. We also have some guests from overseas. You can't see them, and they can't see you because they're on the laptop facing the screen over here. But when it comes to question time, we're going to plug the laptop in, we'll flip it around, and then you guys will get to see them as well. We are streaming this live on our website and several others. So if you want to tweet and let your friends know on livingmaths.com, they can watch it while we are here. But I think before we begin, I would like to introduce the director of the Cape Town Science Centre, just to say a few words. So let's give Judy Kedlin a warm round of applause.
Good evening, everybody. On behalf of the staff and all of us at the Science Centre, thank you so much for being here. And it's my opportunity to give gratitude to the people that give freely of their time and to come and talk to all of us about space and other interesting science events and things. And also to thank our partners who make it possible. And of course, teaching the following that. As I listen to doing things to the Science Centre for us. Also, I think that's someone organizations in view of entry fees. And I just want to say thank you very, very much to Providence College who gave us 5,000 rand tonight towards our Mars rover exhibit. There's our Martian rover, or Mars rover rather. It's a model of curiosity, and you've all seen the footage that's been played tonight. But we're raising funds to build a Martian playpen for him. And thank you very, very much to Providence College. We have got donation boxes, so please feel free to empty your pockets. I'm not shy. Just a few other things. I just want to say that we've got some very exciting things lined for the Science Centre in the future. Our auditorium is nearly built. We'll be ready by the end of April, so we'll see you all in there, and maybe not out here, but this is a nice crowd tonight. We have an exhibition being launched in early May called Great South African Inventions, and we hope to see you back for that exhibition. And also, we're also one of the lead organizations in a really exciting project called Africa Coding. It's about stimulating coding amongst the youth. I can see some frowns. Please don't frown. Please rather just go onto our website and join the Africa Code Week database, and we'll send you all the information about this. It's really exciting. It follows the example of the EU Code Week, and we hope to see many of you there as trainers and as people taking part in the Code Week. But you didn't come here to hear me, so I'm going to pass over to Steve. Thank you very much.
Right. I'm going to call up the very special Teddy Taylor, the US Consul General, who is going to say a few remarks, and then we will and then we will introduce our special guests. Thank you.
Good evening, everyone, and I recognize I'm standing between you and space, so I'm going to get out of your way very quickly. But we're very pleased and privileged to have some of our best and brightest stars in our scientific community here to share with you this evening. We've heard about Dr. Stofan being chief scientist and advisor to our NASA administrator, Charles Bolden. So she's at the top of the line when it comes to talking about these issues and just making the decisions on what NASA does and how they invest their money. And anytime you can have a living astronaut colored, Dr. Coleman, someone that's actually been to space and can tell you what it's like. I saw the presentation earlier today. I think you'll get a real kick out of it. I know I did as a Star Trek fan. And you will find it very enjoyable. But most importantly, what this is doing is it's trying to emphasize to the young people the importance of science, technology, engineering, and math to any society. These are the best paying jobs in most societies these days. And there are also the jobs that, despite the fact that you see two women here, that women are largely locked out of in a lot of ways. And hopefully you young ladies will hear something here this evening that will inspire you to understand that the world is your oyster, and all you have to do is reach in and pull out your pearl. And that's what these two women have done. We had an earlier conversation about math today, which I thought was very interesting, considering we know math, how much a part math is of what it is they do in their particular fields of endeavor. So without further ado, I'll give it back to Steve, or will I give it to Dr. Stofan? I'll give it back to Steve, our Master of Ceremonies, and thank you for sharing this with us this evening.
Okay, so while Cady, you want to just check to see that the laptop is working, we're going to introduce Dr. Stofan. I must tell you that I had the privilege of spending the past week with these two exceptional scientists at the Grantstown National Science Festival. It has been an absolute blast, and of course, if you feel a little bit left out, that you never got to go to the SciFest and see some of these excellent speakers present, the good news is, if you go to livingmaths.com, all of the big talks have been uploaded onto our website, including some of the talks from Dr. Stofan and from Dr. Coleman. We're hoping we're going to get through a little technical hitch. Is it picking up? Not picking up? This is looking good. We look at that. Problem, well, that was almost a problem solved and a problem created at the same time. All right, so I think we should give Dr. Stofan a very warm time. Welcome.
Thank you so much, and thank you, Consul General, thank you to the U.S. Consulate for supporting some of us to come here from NASA. Thank you to Steve and Living Maths, and certainly thank you to the Cape Town Science Center for having us here tonight. You know, people always say to me, what's the favorite part of your job? And I answer very sincerely that it's actually being able to come out and talk to the public, talk to kids, especially kids from all around the world, about the amazing things that we do at NASA. And you might say, well, why don't you just not talk to audiences in the US? Well, because the problems that we're trying to solve, whether it's getting humans to Mars, like Cady and I are going to talk about, or whether it's how to deal with climate change, these are problems that affect the entire world. And you know, the next really smart person who's going to come up with ways to solve these challenges is probably not going to be from the United States. It might be one of you learners who says, you know what, I have a new idea maybe about how to generate power. Or I have a good idea about how we can help the astronauts up on the ISS. So that's why it's important to me to go out and really talk to audiences about all the amazing science that we do at NASA. Now, in my background, I'm a geologist. So I really like rocks. Everybody teases me because I'm a rock person. My husband always says, do we have to have rocks in every single room of the house? The answer to that is yes, of course. So I study volcanoes on Venus, Mars, the Earth, and one of the moons of Saturn. But as chief scientist of NASA, I get to look across all of the science that we do at NASA. And I like to summarize it this way. We look outward, inward, and homeward. Now, outward is the part you're probably the most familiar with. We look out at all the planets of the solar system, out at the universe, out at the galaxy. Looking inward is the part that most people are a little less familiar about, and Cady's going to talk about today. We're doing all this research up on the International Space Station every day, trying to understand how to get humans to better deal with the risks of living in microgravity. When you get up there, I hate to tell you, your immune system loses function, your cardiovascular system doesn't work the same, your bones lose density. And so after hearing that list, some of you might say, well, maybe I should just stay home. You know, why do I want to go somewhere? We want to go to Mars. We want to send scientists to Mars, and I'm going to talk about why in a little bit. It takes 8 months to get there, 8 months to get back. We've got to have our astronauts healthy and strong and ready to work when they get there. So we're using this time up on the International Space Station to do research to try to say, how can we mitigate, how can we reduce those effects so that humans can explore Mars and stay healthy at the same time. Then we look homeward, and I'm going to come to that at the end of my talk. We have 19 satellites in orbit around Earth. You might say, well, why do we need 19? Why do you have 9? Because the Earth is so complicated between the oceans, the atmosphere, the weather, the land surfaces. We need to make measurements in all the different parts of the electromagnetic spectrum, looking at the Earth with different kinds of eyes to try to figure out the complex processes that take place on this planet. All right. So this slide sort of summarizes all the different areas of science. This is basically how we're organized. And the fun part for me is while you look at all these different areas, often the exciting science occurs at the boundaries between different areas, and I'll talk about that in a minute. So we study the sun. The sun is an amazing star, and to be honest with you, there's so much about its behavior that we just don't understand. You get these massive explosions on the surface of the sun, solar flares, really large ones are called coronal mass ejections. Those explosions produce a wind of charged particles called the solar wind that comes towards the Earth. Now the Earth has a protective magnetic field. Those particles generally stream around us and move on, causing the beautiful auroras that Cady's going to show you later. But if it's a big enough explosion aimed directly at the Earth, it can actually damage our communications satellites. And so from a practical point of view,
Hey, Jen.
Hello.
Yes.
Hi. Somebody muted us.
Why they mute us?
Hi from Oak Park. Hi.
When you guys are talking, we can't hear the NASA lady talk.
What?
That's why I muted you. Sorry.
What?
No, that's okay. We just lost the picture. We only have you now.
Anyone know what happened to Mr. Sherman?
Yeah, let's look at us. Hi.
It looks like we all lost Mr. Sherman.
Yep, I don't see him.
I'll go jump on my Skype and see if he's saying anything over there.
Okay, let us know.
Okay.
Thanks.
Steve.
Oh, hold on, they're back.
Wait, they're back. They're back. They're back.
Oh, here we go.
How did you get here, and how does our universe work? But really, it's those simple questions that are the ones that we still haven't answered. You know, for millennia, people have wondered, is there life beyond this planet? So these are the questions that drive us. And I like to talk about it as origins and evolution. What's the origin of the universe, the galaxy, our solar system? And how have they changed or evolved over time, and how can we use that information to better understand what might happen in the future? If you look at our own solar system, and I like to tell kids, you know, when I was a kid, we had 9 planets. You guys only have 8 planets, sorry. So poor Pluto, right, it got demoted because it was too small. So we have our inner planets in the solar system, then the gas giants out beyond, and poor Pluto out here, which in July we're going to get our first look at ever with the New Horizons spacecraft. So we're really excited about that. July of this year, in fact, starting in April, we're going to start getting images that are better than the ones we're able to get with Hubble. So stay tuned. Pluto's going to be cool. We have no clue what it looks like. But when I was in school, we had models that explained, and my kids say that was back in the days of the horse and buggy, but I'm not that old, thank you. You know, we had models that explained why you had gas giants further out from the sun and rocky planets close in. But as we developed the technology to find planets around the other stars, the first technology that we really had was to find Jupiter-sized planets. And we found them really close to their parent stars. We found them in all kinds of weird orbits. And even though our models have maybe explained a lot about our solar system, we now, with many solar systems, knew that we needed new models. Then came something called the Kepler Space Telescope. Kepler is a telescope we've had for about 3 years at NASA. And in the last 3 years, all these yellow dots represent planet candidates that were found by Kepler. And Kepler had the ability to find make higher resolution observations. So we are now able to detect planets the size of Earth. And what we're looking for is that Earth-like planet around another star. In a few years, we're going to launch a telescope called the James Webb Space Telescope. And James Webb will start looking at the atmospheres of these planets around other stars, looking for things like oxygen, carbon dioxide, water, methane in atmospheres that might tell us that that planet has life potentially on it. So a huge revolution in how we're looking at solar systems around other stars. Now tonight, when you go outside, I want you to put your thumb up in the sky.
Okay, now
there's a star field, but you see these little boxes
we're really
right
good
here.
now.
This tells you the size of the sky that Kepler was looking at. So if you go out and you put your thumb out, you're blocking about the size of the sky that Kepler was looking at. 1,000 planet candidates being blocked by your thumb. So that means when you look at the rest of the stars in the night sky, you're probably looking at planetary systems around all of them. That's waiting to be discovered with our better and better telescopes that we're developing and launching over the next 10 years. So while we're impressed by these thousands of planets, it's going to be tens of thousands of planets for kids to study over the next 10 to 20 years. Again, a whole revolution in science we're right on the verge of. But if we're looking for habitable planets around other stars, we also want to know what's the chance of life in our own solar system. Now, okay, we already know, like, no little green men, right? All right, we know there's not giraffes or plants or anything else. We know that from our survey of the solar system. But we know that there were conditions that exist on several bodies around the solar system that have had or have currently or had in the past liquid water stable on their surfaces. We think that liquid water is really critical to the formation of life. So we have targets like Mars. This is Mount Sharp on Mars, which our little Curiosity rover is climbing up right now. And for a geologist, this is the most exciting thing ever because, you know, to us, these layers of rock are like pages in a history book. And as Curiosity climbs that hill, it's reading each of those pages by doing chemical analysis, by looking at those rock layers. So far, what it's told us is that these conditions in Gale Crater have been pretty benign. Lots of water, pretty stable on the surface, not too acidic, good conditions for life. So we're pretty excited about that. Our next big target is Europa, moon of Jupiter, which has an icy crust. Underneath that is a liquid water ocean. And at the base of that liquid water ocean, we think there are volcanoes erupting. Now, there's vents on the Earth's ocean floors called black smokers. Those are really rich environments for life. So we wonder if a similar situation could exist on Europa. This is Enceladus, which is a moon of Saturn. It also has that icy crust, subsurface liquid water ocean. Its water ocean erupts through geysers, through cracks through cracks in the surface. We've actually flown the Cassini spacecraft right through those geysers, and we've measured water and really complex organic molecules. But our mass spectrometer, our instrument, isn't good enough to tell us exactly what those organic molecules are. Europa also may have erupting plumes, and if we could fly our new spacecraft that we're going to launch in about 8 years, maybe we'd get a little bit closer to answering this question of, is there life elsewhere on the Earth? Ultimately, we'd like to go to this moon, which you can hardly see here, but this is Saturn's moon Titan. And the important thing is that little bright light you see at the top. That's sun glint off of an alien sea. How romantic does that sound? Sun glint off of an alien sea. So Titan, 94 degrees Kelvin on the surface, so cold, 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 cold. It rains liquid methane and ethane on Titan, which forms rivers and seas. That liquid evaporates back up into the atmosphere, rains back down in a cycle just like our water cycle. But again, at those temperatures, it's not water, it's basically liquid gasoline. So could life be there without water? We don't know. But again, the exciting thing is, just like with all those planets around other stars, in the next 10 to 20 years, we're going to get so much closer, if not absolutely answer this question of are we alone? And it's going to happen in our lifetimes. And how exciting is that? Really cool stuff. So Mars, though, is the primary place we want to go. Lots of places to go explore on Mars. But you know, it's going to be hard to find that life, because that life is going to be probably fossil evidence, and it's only going to be a few cells across. So how are we going to find it? Maybe our rovers will do it, but maybe not. I have a bias, because I'm a field geologist that goes out and studies volcanoes, that it's going to take future astronauts on the surface of Mars, starting in hopefully about the 2030s, which is NASA's plan. So I see people in the right age range to maybe be future Mars astronauts, to go to Mars and really have a lab on Mars and really study the surface to see if we can find, did life evolve? Does it have cell structure like ours? Does it have RNA and DNA? How different is that life from life here on Earth? Such fundamental questions. Now, before Cady talks, I wanted to talk for a minute about those 19 satellites and what we're trying to do to understand our own planet. As most of you well know, the Earth's climate is warming. This is data just from the period 2010 to 2014. And the reason it's all yellow and red is because this has changed from average surface temperature. And you can see the globe is getting warmer and warmer and warmer. And it's not uniform. For example, it's getting much warmer in the Arctic, which is causing us to lose sea ice up there. So really an alarming situation. So what is NASA doing? Well, we collect with those satellites data, information, for example, on sea level rise. What's the height of the ocean? What's going on with rain? That's important for both understanding drought and understanding flooding. Natural hazards, flooding, landslides. How are vegetation patterns changing across the surface? And how can we use that information, for example, give our data to farmers to help them understand what's the best field to plant in? Where are areas where there might be food shortages because the soil is too dry? All of our different spacecraft are gathering this information what we're increasingly trying to do is to make that information available, not just to scientists to study problems, but to say, okay, how are people who have to make decisions about where to put the next building along a coastline where the sea level is rising, how do they make that decision if they don't know how to use NASA data? So for example, next week in Pretoria, actually it's this week in Pretoria, we're conducting the U.S. is conducting a workshop with the U.S. Agency for International Development for people from all across Africa to help learn to use some of our complex NASA data sets to help address these problems. So we're trying to make the data not just available to scientists, but available to everybody, because climate change is so important to deal with. Now, one of the things we're also trying to do is get more and more people involved in what we do. We have this website, nasa.gov/solve, where we have challenges and opportunities for the public to either take NASA data and actually help process some of the data. In some cases, for example, we've taken so many images of stars that to classify them all, the scientific community can't do, so we ask the public to come help. There's Mars projects. There's all kinds of projects that, frankly, you could spend a half an hour a month, or we have actually people who have classified over 200,000 stars for us, non-scientists. So these citizen science projects, which you can find on this website, are a great way for everybody to get involved. And it is so important for everybody to be involved, because again, as I said in the beginning, you know, the person who's going to solve our next big challenges isn't necessarily going to be a person from the US. It might be somebody from South Africa. So I challenge you guys, especially the students in the audience, to work hard at math, even when sometimes it seems not very fun, to really study physics, engineering, because these are great fields to get into. You get to do fun things, like work on things like maybe the Square Kilometer Array, or for the South African Space Agency. So think about those kind of careers. And now Cady is actually going to tell us about what it is like to live in space.
Okay, let's see. Do this, and Steve, is it better if I stay here?
It's up to you. Whatever you comfortable.
Okay. Thank you. Okay. I have all my tools precariously perched. I have one more thing to do. How many astronauts does it take to plug in the computer? Apparently more than me. And not quite, but there's a little switch on there. So.
I must have switch on.
Yeah.
This one?
Yep. I asked Steve when I said, if I plug this in, are all the lights in the building going to go out? I was worried. Okay. This is where I used to live. The International Space Station. It's orbiting above our heads. In fact, it's going to be directly over our head at 7:58. Isn't that pretty cool? I don't know if you know that you can go out and watch the space station pass over, and I really encourage you to go out. It's actually a better pass, I'll tell you, tomorrow night. Tonight it's kind of low in here in the city. Might be a little hard to see, but tomorrow night the space station will pass over at 87 degrees. It's almost straight up in the sky, and it'll be the brightest star in the sky. It doesn't just zip over. It's actually, it just kind of crosses like this. And so you go on our website, or you just Google ISS sightings or space station sightings, or I want to see the space station, where is it? All those things will lead you to this page. You put in your country and your city, and it will tell you when you're going to see it, exactly, like that minute, for how long, and the most important thing, what direction you should start looking and how high. So we're using that map, right? Where you have to know, well, 20 degrees, that's kind of low, and in the city it might be hard. But as soon as you get above like 30 degrees or so, you're going to look in that part of the sky, and you're looking, and you see nothing, and you think, you know, I'm not see it. And then suddenly, in that space, you will see something moving. You have a bunch of false starts where you think, is that it? Oh no, well maybe, oh well. And then, I'm just telling you, it goes through everybody's minds, even me who knows it's coming. And then you will just see a bright star that is just cruising, just sailing. And there are, tonight, 3 people up on that space station. And starting Friday, we'll have 3 more. And so we're usually a crew of 6, but the new crew comes on Friday, this Friday, and that's going to be pretty tremendous. It's actually my crewmate, Scott Kelly, and I went up there for 6 months, which I would have stayed another 6 months in a minute, but Scott is going to get to stay for a year. Every one of you should want to be up there. It's amazing. So let me tell you about it. This, there's the space station. It shows you how big it is. Let me find a pointer here. There's a pointer. And so this part here with the solar rays are a little bit dark in this picture. This part is the long part. It's outside. There's our robotic arm. But we live in this part that kind of goes down the center. And each one of these modules, we call them, and there's about 10 of them. I never count. I just kind of go. But there's about 10 of them, and each of them is the size of a very large passenger bus. So not like a small school bus, but a large bus. And so they're very, very big and without the seats in them. So it's really exciting to move around up there. Now, what you may think of more often in terms of spaceflight is that it's going to be really tiny and cramped. And that is actually true, but it's for the way up. And so here is our launch pad. We launch these days with the Russians. We're an international space program, and there are about 16 different countries involved. There is Russia, the United States, Canada, Japan, and a whole bunch of countries in Europe. And we are right here. This is the launch pad, the very same launch pad that 54 years ago next week, Yuri Gagarin launched from. 54 years of human spaceflight. And I was up there about 4 years ago, so we were actually up in space on that anniversary. This is that launch pad, and the capsule is right in this part. The capsule is actually a pretty small place, and we're going to see a little film about it. But this is the part, sort of like the size of a smart car that docks to the space station. And then this part right here is where we are actually all 3 of us in there, and you'll see that. And then there's a propulsion part. But the whole thing is about the size of like 2 smart cars, pretty small. So it's a pretty small place to go with a couple of people who may or may not be your closest friend. Okay? And so but we're not friends. Generally, we don't get to pick who we're assigned with. In fact, we just definitely do not. And the mission is actually just more important than that. It's more important than whether you like each other, or you know each other, or you want to go with them. And you know what? Any mission, any crew is a good crew and a good mission. So I was there with Dima Petratia from Russia and Paolo Mescoli from Italy, and then we joined Scott Kelly and his 2 Russian crewmates. And so we formed a crew of 6 people. And so here's Scott. Oops, there we go. Here's Scott Kelly, who's launching again on Friday. We are so jealous, the rest of us, just totally jealous. And there's myself, Paolo Mescoli, Dima Petratia, Sasha Kaleri, and Alex Pipochka. So we all speak a combination of English and Russian. It kind of depends what we talk about, but all of us are qualified in both languages. It's a requirement. So a little short film that shows you a little bit about the launching process, which was pretty exciting. Some of you might have run into my son tonight and see him in this film here. He was 10 when I launched to space. We start off with just getting oriented. This is the space station. This is a real movie. It is not virtual reality. And to me, it looks like a cartoon, but I know it's real. The space shuttle took this footage when it was actually backing away from the space station. But here we are, getting ready. We're in that small capsule. We're doing things in our spacesuits, in our U.S. spacesuits. Those weigh about 150 kilograms. So they're pretty heavy. We do all that work in a swimming pool. But there's a couple years of training, and then we are ready to go. And this is launch night. I'm waving to my family. And there's my son Jamie and my husband, Paolo's wife. We're doing final pressure checks. We're always checking everything. And now we're going to report in. I begged the guys to take small steps and walk slowly, and they forgot. Yeah, we're all a little nervous. I mean, we're going to space. But there we are on the launch pad, and now up in this tiny little part. And it was just before Christmas in 2010. It's just an amazing, amazing place to be. Whenever this happens, I mean, even though I've done it twice before, I launched twice on the shuttle, there is something very, very profound about being in a rocket on your way to space. It's not that it's so violent, it's just that it's so sort of relentless. Once you launch off that launch pad, you realize you are just like never going to stop until you get here, which is the International Space Station. I love this scene because it shows you what it's like to fly up there. And that's what we do every day, all day. There is no walking. It can't be done unless you really kind of work at it. And why walk when you can fly? It's leading the life of Peter Pan. This is us, Paolo and I, capturing the Japanese supply ship. And we actually did that in a very, I know I have very good space hair. It is really good space here. These origami are because right after we captured that supply ship, they had that very large tsunami in Japan. And so many friends and colleagues were displaced. The Japanese control center was shut down. It was a really very traumatic experience for everyone. We were glad to do our part on the space station by taking pictures of Japan to understand at night how much power was left and where it was in Japan. And those white cranes represent hope and rebuilding for the Japanese people. Well, a few weeks later, we're back at work, and so are some of our Japanese colleagues. And this is the space shuttle coming up to visit, but actually to bring that big, large module right here. And that's a new piece of the space station that's going to be used for storage of new pieces of equipment, experiments, everything. So the shuttle is doing a little sort of pirouette in front of us, showing us all its size. Paolo and I are frantically taking pictures of every surface because those pictures will actually be used to analyze the integrity of the heat shield of the shuttle to make sure it's safe to go home, to make sure no damage has happened on ascent. But after those pictures, the shuttle docks. We do all those pressure checks. This is what it looks like from the outside, and then our friends are on board the space station. And they are here to do a lot of work. There's a little fun and handshaking, and they bring some fresh food, which we're pretty crazy about. And then we are up in space, doing spacewalks, attaching that new module, using the robotic arm to pick up big pieces like that and attach them to the space station. And then the shuttle crew goes away, and it's back to regular work. We have a new robot up on the space station. It was our pleasure to welcome Robonaut to the space station. He's the one on the left. It's a great picture of Scott, I think. And this is a picture of just cruising through the space station, actually sped up. It's faster than we would fly when all the grown-ups on the ground are looking. I'll put it that way. And you can see how much stuff is up there, and that there's a lot of experiments to do, but there's also just normal life. This is our dinner table, and we're actually pulling up to watch the new crew launch, because Scott and his crew have gone back to Earth and landed. The new crew was gonna launch, and it's just time for a lot of work. I would say it's an amazing amount of work up there. I would say we work really most of the time, so to speak. But there's always time for a little fun. This is a box of chocolates that folks sent to us. You'll notice there's only 5 pieces of chocolate that are floating there. The rest of them have been dispatched. And actually in the background here, see these boxes, these are all of our food in the background there. Well, a little science, a little magic. In some ways it seems like they're the same. This is a world up in space, on the space station, where the rules are different. And we are taking advantage of that. Folks on the ground and we in space are always trying to think, what can we learn in a place where some things are profoundly different? And the biggest thing that's different is gravity. We actually do have some gravity up there, but it's such a small amount. 10 to the minus 5th or 6th, like a 10,000. It's really, really small and tiny because we're so far from the Earth, about 400 kilometers up. And so this picture of a water drop with a bubble in the middle shows you we're looking at what liquids, in this case water, what do liquids really want to do? It's a hard question down here to find out. I mean, we can, if I take water from a pitcher and I pour it into a glass, we know that hopefully if I'm aiming correctly, it's going to end up in the glass or it's going to end up on the ground, but we know what direction it's going to go. It's going to go downhill. It's going to go down. Well, up in space, go up, go down, weightless. Without that big, big dominating force of gravity, we get to see, what about the tiny forces, the ones that are just overwhelmed by gravity? We get to understand the tiny forces those tiny forces may not seem significant down here on Earth, but they actually are for every process that involves flow through a pipe, whether it's a sewage pipe or a pipe in a factory that's making something. Everything from plastics to food to metals to glasses. Everything that is flowed through a pipe, including in our bodies, our veins and arteries, that's flowed through a pipe. And even things like, let's say we wanted to have what I call a lab on a chip. Let's say we wanted to be able to find out how a person is doing with respect to health, somewhere out in the field where there isn't a lot of medical tests that are available. We have a little slide, we're going to put a little drop of something, maybe blood, whatever, on the slide, and we're going to see what happens because we're going to analyze that. And where that little drop is climbing up that slide and interacting with the stuff that's on that slide, those are the tiny capillary forces at work again. So we need to understand the small forces down here on the ground, and going to space allows us to do that. Same thing goes for combustion. Over on the left, we have the Earth candle flame that you're very familiar with, and then over on the right is the space candle flame. And the big difference is that when those lighter gases are produced at the wick, when you light that candle flame, those gases here on Earth, well, they're going to go up. And then new fuel is going to come in. It's a really dynamic situation. Combustion happens quickly, and it is complicated. And we have to make measurements about these kinds of flames, many measurements in less than a second. Well, without that, without the lighter gases rising, what we find out is that things happen a little more quietly, a little more slowly. We make those same measurements over almost a minute. So we can find out things about combustion. And in fact, we've discovered that there, in some cases, is secondary combustion, a second ignition of when things are burning. And it's always just happened too fast to see down here. We didn't have the right circumstances. So we're finding those circumstances up in space. We're using that to understand fire in space, but also combustion here on the ground, the formation of pollution, of soot. How are those things formed? So space lessons leading to Earth benefits. We have another example here is crystal growth. Crystals can be used for anything from designing a new drug for a disease, like you see on this slide here. We see the ugly Earth crystal. I mean, it's actually pretty beautiful too. And then we have the space crystal that is more perfect because without gravity, having those molecules that are trying to sit down one after another in a really orderly way. Well, down here on the Earth, one of them might sit down crooked, and his friends don't know that he's crooked. And so we end up, we have defects in our crystal. So the perfection allows us to discover new things about crystals. Same kinds of crystals, or different kinds of crystals, but crystallization can be used to understand computer chips and how to have defect-free computer chips or what materials to make them out of. Growing plants up in space. We needed to go to Mars. Dr. Stofan talked a lot about the hard road to Mars. Well, it's going to involve food. We're going to have to feed those people, and we're going to need a really big spaceship if we have to bring all the food with us. So we need a way to have food up there in grown in an environment where there's not a lot of water. There's energy is in short supply, and there's not really a good soil to grow things in. Sounds kind of familiar, doesn't it? We've got some earth problems like that. We also can find out about people's bones, my bones included. And we up in space, we actually lose bone, much like people who are older that have osteoporosis. So a woman who is 70 years old who has osteoporosis, the amount of bone that she loses in a year is what I lose in a month in space. It's very fast. So that sounds like bad news, but the good news, it happens so fast, it's really easy to observe and to measure. So we can do tests that help us find out about this really important disease. And I can only share my own medical results, but I will tell you that I came home with all of the amount of bone that I left with. Really, like almost exactly. Doesn't mean my bones are the same, and we're trying to understand that as well. And I'll have tests every year of my life. I go back to NASA for a physical. That disease, osteoporosis, affects mostly women. I like to show you my other pals up here. This is Sandy Magnus. Peggy Whitson was the commander of the space station. Pam Malroy They were not on my mission, but on other missions, and it was really neat to have a crew that had actually so many women. Ellen and I have been talking in schools all over Cape Town today, and I end up spending a lot of time talking about people and being on teams and how you have to really let people surprise you and work hard to get to know them. And I think that we find that women and men and people who don't look like us have different ways of doing things. And as long as we understand that, boy, they might bring more to the table than we do in some respects, and that we all have to respect each other's gifts. And we have to constantly, if we want to solve the hard problems that Ellen talked about, we need to constantly be looking at our friends, looking at people who are not our friends, people that we almost don't even like, looking at them and realizing, I better know more about this person because we are actually on the same team, and I need to understand them to solve problems. Back to the osteoporosis, we actually do a lot of exercise up there. That's part of the reason that I came home. And so the good news and the bad news is that exercise is here to stay for every single one of us, young and old. It really leads to a healthier body in space. We don't actually do it this way. We do it this way, upside down. We're lifting weights upside down, and it works just fine. This little film is just fun. But it does just show you a little bit about living up there. There's Mike Fossum on the treadmill, wearing a harness to hold him onto the treadmill, otherwise we'd be bouncing off the ceiling. Taking a little shower. That doesn't look like a shower, does it? No, we don't have one. And yet, we're clean up there, I promise. We just take sponge baths. There's Mike climbing into his sleeping bag in his little cabin. You always have just as much privacy and everything else as you need up there. There's Satoshi doing some science experiments. We're always using our safety equipment when we're supposed to. It's just the way you're supposed to do things, and it works out. It's just what we have to do. We have to be safe up there. You're looking out our beautiful window, looking down on the earth, seeing mostly ocean, as Ellen discussed, and some clouds. And now for a little bit of fun. Looks like Sergey and the guys are floating backwards. They're going that way. But actually, think about Sergey being still, and the space station's going this way. And the last thing, my friend Satoshi, he loves baseball. Really, like a lot. But everybody's busy doing experiments, so he has to play by himself. So now he's leaving the picture. The batter and the catcher. Now, the engineer in me and the crewmate was actually pretty concerned about the fate of the flashlight he used as a bat. Okay. I know. Pretty fun. Well, speaking of fun, it's a wild place up there. They never even knew what hit them. I like to show it twice. It's fun. We actually brought gummy worms, gummy bears, gummy Swedish fish to see which ones were the best. Some more of my buddies up in space. I like the kids to understand that before you go to space and become an astronaut, you need to be something else first. And so Stephanie Wilson is an aeronautical engineer. Tracy Caldwell is a chemist. Dottie Metcalf, a teacher. And Naoko Yamazaki is an engineer as well, aeronautical engineer. So lots of different kinds of careers. But when we get up there, we're just people, just like everybody else. And we bring our, we just have to do what we like to do for fun. I like to play music. I'm not the best player in the whole world, but I think music is really universal. This is my friend Ian Anderson of the band Jethro Tull. I say friend, but I actually never met him when we played this duet between Earth and space. Isn't that cool? So I also got to consult for the Gravity movie a little bit. My brother met Sandra Bullock, Sandra Bullock's brother-in-law, when I was up there. And she told me every time she saw me on TV, she wanted to give me a scrunchie. For my hair, like a rubber band for my hair.
International Space Station. We should remember that today's cosmonauts, scientists, and astronauts are still every bit the rocket heroes they were 50 years ago.
So from the cultural city of Perm in Russia, let's salute Cady, Dima, and Paolo up there in orbit. And of course, the legendary Yuri Gagarin. Go safely.
I mostly like you to see the flute getting sort of going back and forth. You see Ian's holding his flute, and if he drops it, I mean, that's a bad thing. But the flute, actually, it's really just kind of fun to pass it back and forth. Well, I want to just take you on a little tour of the world before we stop for questions. And so here's our space station, and there's our window, taking pictures, and taking pictures of a place I think you'll recognize. Isn't that beautiful? So, just try to point right in here. So here we have Cape Town, Cape Point. So we're somewhere right in here. Isn't it beautiful? And for me, it was very important. I mean, we see these places from space, and it's so special. I mean, it's just, it's hard to describe the fact that, you know, when you go to the window, you can look down at the Earth, and you'll see everyone you know and everyone you don't know. And I think all of us are changed in some way by that. It became a little hard for me to just really just feel like I was from a country. It just seemed sort of silly in a way. I'm very proud of being American. I'm very proud of what I do, and at the same time, you know, I think it's really clear that it's one big planet, and it's ours, all of us, to take care of. I'd love to show this. This is faster than we actually go. It's sort of stop-action photography. But you can see what the Earth looks like going by. Those are the nights, the city lights. When you're first learning your geography up in space, it's a little bit easier to find your way big city by big city. If you're over Egypt, it's really clear where the Nile is because people are living right along the coast there. And then you can see there's a lot of ocean on that planet. And look at the atmosphere. See how thin that is? Just really, really tiny. We can see fires. I like to point out this is a fire right here, and here, and here. And so when you had the fires in Cape Town just recently, we were up in space, they would be able to see those fires easily. So it's a little faster than we go, but it gives you an idea what it looks like to cross the planet. It takes us an hour and a half to go around the world. And there's Aurora Australis. Those are real colors. It's really beautiful. I urge you to go to the internet and see. It's a little bit harder to see up here, but go to the internet and look for the gateway to astronaut photography, and find the place that you live, find the place that people that you care about live, and look at on the bottom half of the page. There's the videos, and again, this very, very small layer of atmosphere that is really our only protection for our small planet, and that's the kinds of problems that Ellen was talking about that we're trying to solve at NASA with our ability to take these pictures. I think it's a very human thing to look back at the planet and capture that. And at the same time, it's an incredible scientific thing for us, not only to the astronauts taking pictures, we have high definition video on the space station all the time, streaming down to the Earth. And so it's our way of observing the planet, and that's a lot of information. And just next week, there's a conference in Pretoria that will be part of a very big effort to organize the information that we have. We've just released, I don't know if Ellen mentioned it, we just released a lot of information about elevations all over the world, a survey, and so we're trying to make sure that that information that we have is really well shared. But let me just take you home through landing. The three of us climb into our tiny, tiny, tiny little spaceship, designed by very good engineers. We land with a parachute. Doesn't look good, but it's not bad. And through your sheer science, physics, and math, you can see that we've got a line here. This is the angle that our spaceship came down through the atmosphere. This would be the part that was burning up on purpose. Because we figured out a way to coat a spacecraft with a material that as it burns up, it actually sort of seals in place. And we figured out exactly how much to put on there that isn't so much that is too heavy and we come down too fast and we burn up. And so it's an interesting miracle of physics there, where these are people that did their math, and I'm glad they did. I landed just fine. I tell people that the bigger they are, the harder they fall. So it turns out that those of us of smaller stature are doing okay. And 30 minutes later, I was talking to my family. It was nice to be back on Earth with my family, to see the places, and not only just to see the amazing view, but also sort of to be part of the view was really important to me. And I think for all of us, it comes down to families. If these kinds of things are dangerous and they're hard, and it doesn't matter whether you're an astronaut going to space or you're one of the other people that work for NASA that is up all night in mission control away from their families, or even traveling in South Africa away from their families. I actually did bring mine with me. My son is here, just 4 years older than that picture. But it was nice to leave them with his great dad and our trusty cat who actually thinks that he's a dog. That's Bang. Bang thinks that he's a dog, and so we humor him. He's not crazy about the snow, but. And here at the Science Center, I want you to keep this picture in mind, because this could be any of the kids at the Science Center and the adults. I came across adults at some of these science stations having the best time figuring things out. And so the kids realize that you look like this too. This curiosity and just proud, like, hey, look what I have. Look what I have that I think is so interesting. And kids, it's your job to keep asking questions and telling adults what you figured out that's so cool. And adults, it's your job to realize that they are the future. It's our job to be their leaders and the people who support them. And I think the Science Center here is a great place for that. When this picture was taken, this is President Obama and my whole crew. And when I was in 3rd grade, nobody knew I was going to be in a picture like this. You don't know which one of the kids in this Science Center, which one of the learners here in South Africa is going to be in a picture like this in the future. And they don't know either. That's why all of us have to be ready for the future. All the kids need to be doing math and science. All of us need that kind of background because we have places to go. As Dr. Ellen said, we're going to be going to Mars. We're not ready yet, and that's why we're using the space station as a test bed. We'll be using the moon, which is only 3 days away. So let's see, space station, 8.5 minutes away. The moon, 3 days away. Mars, 8 months away. I'd just as soon learn our lessons here on Earth and about 3 days away on the moon or on an asteroid. And then when we learn those lessons, we'll be ready to go on this journey. Probably won't be Ellen or myself, but it could be somebody who's in this room on the younger side. So thank you very much, and we look forward to your questions. We'll give a shout out to Dr. Cady.
Right, can we get the lights on, please? Oh, wait, I'm able to get the lights on, please. And we're going to try and turn around the laptop over here. We've got guests from quite a few countries. Whoops. Okay, I'm going to leave the computer facing you. Is the audio working in the laptop? Audio in? Ah, here we go. It's working. It could be. That makes no difference. I'm just going to try and get this through. Okay, let's see. Right. And we're going to turn up the volume because we've got a whole bunch of people over here from all over the world. Can you guys hear us? You can hear us? Do you want to maybe one of you just unmute your mic so we can hear you?
Who's hi?
Okay, so that's great. Okay. All right. Plug it in here. Then you can see what.
They control it. I think they control it.
Hey, Krista. Okay, it's working. And we can also see some of the questions that they are typing over there on the screen. That's great. So are you guys in the screen? Yes, you are.
Put up your hands if you want to ask questions. Right in the middle.
They're still mute. Oh.
They shouldn't be.
Smile.
Smile.
Okay, you can see his face.
You can breathe quiet.
Oh.
When I was growing up, I'm 50. I was born in 1960, and it wasn't something that girls did. And so it wasn't that I my whole life wanted to do this. It wasn't until I was about 20 when I met Dr. Sally Ride, the first American woman astronaut. And it took seeing somebody that looked like me, somebody that that I could relate to, where I just thought, wow, I want that job. But something that's universal for all of us is that we've done our best to be prepared. When you're your age, and you're at school. I mean, I use the things that you are learning in school, all of you, every single day. I use math, I use writing, I use reading, all those basic things, science, all those things I use every single day in my job as an astronaut. So we're on the right path for that. All of us are something else first. I was originally a chemist, and Ellen is a geologist.
The exciting thing for space agencies is we hire people from just about every background you can think of, from our astronauts or oceanographers, geologists, engineers, doctors. So you have to be really good at something, but it has to be a skill we need, but that covers a pretty broad range of skills. What you have to do to become an astrophysicist, you have to go to school. So people who study astrophysics, usually they work hard at math in school, they work hard at science. Now, I had to, as a geologist, I had to work hard at math. I actually was not automatically good at math. In fact, sometimes I was downright kind of mediocre at math. So I had to work way harder sometimes than other people. But I knew I wanted to be a geologist, and if you know that you want to be an astrophysicist, you have to say, well, I've got to put in that extra effort. And then you have to go and get a first degree in astrophysics, and then you usually have to go on and get a PhD or a doctoral degree, which is what I have in geology, and what Dr. Cady has in chemistry. So it means a lot of school, but a lot of the school is fun, especially that last bit when you're working on your PhD. You get to come up with a project, like, I'm going to study the atmosphere of stars on other planets, and that's what you work on for the last part. So it's not all just going to class and having tests. It's getting to do really cool and fun research. So all the school isn't always like
You can pick right at the back there. The gentleman in the back there, yes.
Excellent. One question. Most astronauts I've heard of have PhDs. Is a PhD a prerequisite for A, becoming an astronaut, or B, working for NASA? And secondly, can South Africans work for NASA? And how to?
So PhD is not a prerequisite. I think it depends on what you do. I said all astronauts are something else first. The requirements are to have a varsity degree plus 3 years of experience, a master's degree plus 2, or a doctorate plus 9. And so it depends on what's traditional in your field, really, because you're just trying to show that you are accomplished in your field. Now, for the pilots, there's a lot of actual flying and test pilot school and those accomplishments. I'd say in the sciences, most people, if we're picking you because you are a chemist, in order to be at that end where you're going to get picked, you probably do need a doctorate, but it's just a certain proportion, maybe 30% of astronauts that have PhDs, not so many.
And it's certainly, we have people at NASA who help build spacecraft, who help take care of our rockets, who don't have university degrees at all. So we hire a huge range of people at NASA. We hire all U.S. citizens, but not. We do hire people with green cards in the U.S. And we also increasingly are trying to make a lot of student opportunities for students to come, maybe on exchanges, to come work at our NASA centers. And that's one of the things, for example, that we're doing here when we're in South Africa and we're starting to work with the South African Space Agency, is to say, how can we do some of these student exchanges to help with training? But I would really encourage you, there's so many opportunities right here. You guys have the square-kilometer array being built, the SALT telescope. There's really exciting opportunities, and those are going to get more and more as the years go by.
You said 5.
Right here?
It's going to come at 5. Okay.
How do we drink water? Well, here in South Africa, do you use those kind of bags of juice where there's a bag of juice and if you want to drink it, you poke a straw into it? Do you use those? Well, that's essentially what we do, except that if we use them just the same way you do, when I squeeze that bag, juice would come out and it would be a big ball of juice and it would get bigger and bigger and bigger. And so we have a way to kind of like close it in half, the straw like this, so that it doesn't come out unless we're ready for it. And we also use those drink bags to take our showers. Literally, that's how I wash my hair. Is I just take one of those bags and I put warm water in it, half hot, half cold, if you want. And then I stick water on my head, a little shampoo, swish, swish, swish. And then I take a towel, dry towel, and I sop that out. And then I put a little water on there and rinse it out. It takes about 5 minutes. It's really, really fast.
Yes.
And so we can use our drink bags for lots of different things.
And watch the tape later.
All right.
So the question was, my bone density stayed the same, and did I put a lot of effort into that, or was it just I have good bones? So I came back with the same amount, and I said that carefully because it's not that they stayed the same. They probably didn't. It's actually hard to tell unless you start listening through and really looking, and we object to that, right? But whenever any of us has a little piece taken out, everybody's very excited to look. But it turns out that probably we're losing bone through this sort of flexible middle. It's kind of like a network in the middle of your bones. And then when we exercise, we're building it back up on the outside. That's the current theory, but we're always testing it. It seems like exercise is really part of the way. And if thousands of people on the ground who are working at NASA and the other countries, if they all know whether you exercised or not that day, it's very motivational. And I actually want to congratulate our question asker because I understand she just got her doctorate yesterday. It's a hard thing. And congratulations.
Before you answer any more questions, I do know that we're getting a couple of questions too. I think we have Mr. K over there from Illinois who wants to know what is the best part of your job, and of course we have Cheryl wants to know obviously what kind of experience do you need, but I think we kind of answered that one. You want to speak about the bone density bit?
Yeah, just quick, and then I'll start that next question. On one of the last flights that we sent up in the autumn, we sent up mice, and one of the things we were doing with the mice was to test new drugs for osteoporosis. So the fact that this effect does happen so quickly in space, we're actually trying to utilize that and do new drug tests. The favorite part of my job, you know, the most fun I've ever had is I worked on a mission called Cassini, which is in orbit around Saturn right now. And a couple of summers ago, we got a pass back across the North Pole of Titan that we had never seen before. This was back in about 2005. We got the images back, and they were covered with these dark blobs, and we realized we were the first people to be looking at these alien seas on another world. And it was so exciting to be able to be, I'm not brave like Cady, you know, I stay here on the ground. So by looking at spacecraft data, you know, for astrophysicists or people who study the sun or people like me who study planets, you know, I get to explore and be the first person to look at new planetary surfaces and I don't even have to take off my pajamas or leave my living room or, you know, get ready to go to work. I can do it on my computer. So, favorite part of your job?
My favorite part of my job, I have to say that it was flying, like literally flying on the space station. I mean, I am not the most graceful person down here, or the most coordinated, and the fact that with the touch of a finger, you could just move yourself. In fact, there's a video on YouTube you can see where Karen Nyberg demonstrated this for me, where you can take a single hair from your head, if you have long hair, and you can put it between your fingers, kind of like dental floss, and use it to push off of something. And if you push slow enough, so it doesn't just snap, if you push slowly, you can use the strength of that hair to move yourself across the entire space station. So it's just so delicious and wonderful, and I loved that.
Okay, we'll take one from the audience, then we'll take one from the internet.
Dr. Coleman, it's an honor to be in the same room as you. I'm a fellow food player as well, and my dream one day is to go to space. How difficult was it
keep your food and chew up on the space station? Well, I was the only one up there, right, with a flute, so by definition, I was in tune. But it's interesting because I left it put together. The flute is traditionally in 2 pieces, and I was just terrified that if I took it apart, then I would lose a piece. I mean, we lose things on that space station all the time. It's actually, not that we do, but actually we're so careful about it, because if you lose the only chord or the only instrument for an experiment, if you just forget that you have it, and sometimes because some things don't really weigh anything, forget you have them. And I was actually having a conference with my, a family conference, but my band showed up. We had an astronaut band, in fact we had 2, and they showed up, and we got to play music together for a while, and it was just it was really fun for me. But then we were just about finished, minutes away, and a very big alarm went off on the space station. And so I just, dropped everything, zipped down to the main computer with everybody else, because our meeting place, looked, it turned out to be nothing, and went back to work, because it was time to go back to work. And it wasn't until I got to be, late at night, 11 at night, and I thought, maybe I'll just go play. And all of a sudden I said, where's my food? I had no idea. And there is a place, because we have a lot of airflow, we have a lot of fans that move and clean the air on the space station. There are a few favorite places that when you lose something, you pray that when you go look at this fan intake, you will see what you're looking for. And there was the flute. It finds you.
Do socks also go missing on the international station?
Well, here's actually a kind of interesting thing. So we don't actually wash our clothes. We wear them until they're worn out, and then we put them in a supply ship, and then when the supply ship undocks with all of our trash, it burns up. And so I tell people this is the ultimate definition of burning your bra, right? And also, the socks were actually all, for people who have feet this long, right? So these socks would come, up to here, and it was just ridiculous. And suddenly it occurred to me, I'm going to throw them away anyway. So I get a new pair of socks out, and I would actually just cut them in half.
Okay, we've got a couple of questions. We want to just turn around there. We've got Martin who wants to know something about keeping in mind that many species are extinct on Earth. Do you think that humanity will really be able to adapt to a terraformed environment, or will we also become extinct, at least in that environment? So you want to address that?
Species extinct, as the questioner asks. It's what species do on this planet. We've had thousands of species that have gone extinct. So if you look at that data and you extrapolate outward, you say logically, at some point humans will become extinct. Obviously, for all of us in this room, we think, yeah, but aren't we smarter than that? Couldn't we find some way to adapt, move, get off the planet? So there are people who talk about things like terraforming Mars. Could we, and there's been scientific papers written on it, could we change the atmosphere of Mars over a period that would unfortunately take probably hundreds of thousands of years to make Mars a habitable planet where you could walk around out on the surface without a spacesuit on? Maybe. I kind of feel like we've already screwed up one planet. Do we really want to go and screw up another one? But we'll see. We'll see. It's certainly a challenge to see whether we could be smarter than all the rest of the species and not extinct.
Okay. Do we have a question from the audience? Yes.
You spoke about trying to find a certain what I'm interested in, I want to know what's the thing to find.
So if you find extraterrestrial life, what do? And I'm sure that there are ramifications.
The first thing is, take a picture. I used to joke, I was designing a mission to float in one of those extraterrestrial seas on Titan, and I always said my favorite moment was going to be when some fish swam by the capsule. So the first thing you want to do, that's a joke, the first thing you want to do is take a picture of it. But really, there's two kind of things we think about. One is fossil life. And this fossil life, obviously, the first thing we're going to do is look at it with a microscope, really trying to understand these basic questions of, does it have a cell membrane like our cell membranes? Does it have a nucleus in the cell? Does it look like our cell? And then try to use that information, because maybe it will, or maybe it won't. We don't know. We know that amino acids, which are kind of the building blocks of life here on Earth, those have been detected on comets and in interstellar clouds. So the building blocks of life on Earth we know have been distributed everywhere, and that's why we have this suspicion that life elsewhere would resemble life here on Earth. But we won't know that until we find it. The other thing we actually worry about is something called planetary protection. where we say, okay, the last thing we want to do is to bring some kind of bacteria back to the Earth. Those of us who are old enough in the room remember the Andromeda strain. It was a science fiction movie. You know, we don't want to bring bacteria back to the Earth that could actually be harmful to life here on Earth. So there's an international treaty that governs going to explore places like Mars, where there's a slim chance that maybe underground there could still be life. So we clean our spacecraft before we go to Mars to make sure that we don't contaminate Mars at this point with Earth life. And then when things come back to the Earth, for example, if we return eventually astronauts or soil from Mars back to the Earth, we will treat it and analyze it very carefully and protect human life from it until we know it's safe. And that's, again, it's governed by an international treaty. All the space agencies of the world have to abide by it.
Okay. You have a question, gentlemen? Back to the...
Okay, so you talked about going to Mars and the geologists that reason why. Surely Venus is like half the distance, and about 50 days out it's got bar pressure and the right sort of temperature. And most of the places where there's the prospect of life now in our solar system are liquid oceans and stuff like that. Surely those would be better places for us to kind of go to than going to this dry, barren rock.
Well, you know, the problem is actually those other places in the solar system are much harsher than Mars. For all that Mars has its issues, you know, it doesn't have a protective magnetic field around it, so you will get more radiated. It is a dry and dusty place. We can't walk around on the surface. But Venus is actually 500 degrees centigrade on the surface.
50 km up?
50 kilometers up in the clouds of Venus, it's much cooler. But there's still sulfuric acid in those clouds, hydrochloric acid. It's still a really harsh environment. And don't get me wrong, I love Venus. Venus is fascinating. For Venus and the Earth, they're about the same size. They're made of about the same stuff. It's like you put two chocolate cake mixes in the oven, and one came out chocolate and one came out lemon. So Venus is we call it Earth's evil twin. You know, why is it this dry, hot, alien world? Really fascinating. So I used to spend a lot of time working on Venus before I took this job. So a fascinating place. So sometimes we do still talk about sending humans maybe just to orbit Venus or to go in, but not into the clouds, because it's pretty dangerous. Places like Europa, where we think there's that subsurface ocean, Europa gets bombarded by radiation from Jupiter. So we even worry about sending spacecraft into that environment because their computing systems and everything are really susceptible to that strong radiation. So for all that Mars has issues, Mars, the Moon, asteroids are probably the most benign places we can find in the solar system right now to send humans. Though I would love to see a human on Titan one day.
Okay, we have a question from Erin Farid, who's watching this on YouTube. And she says, please, can you wave at her? So if you wave at the laptop there, so Erin knows if you're waving. And she wants to know, how hot is the atmosphere in space? Or what is the temperature like in space?
I actually never memorized the exact temperatures, but basically, whenever you are on the side of the Earth that is looking at the sun, it's going to be really hot. You're under, I don't know, plus 125 C, something like that. And then on the back side, where you're away from the sun, then it's going to be really cold, like minus 250. And don't quote me on those numbers. I should go look them up, or you should go look them up. But basically, it's always going to be really hot from the sun and really cold in back, and it makes it very difficult to design spacecraft in that they have to be able to tolerate both extreme heat and extreme cold. And if they're something robotic, have a part like a solar array that's supposed to deploy, it needs to work in those conditions as well. So it's very challenging. And I'm sure that those people that know.
Okay. We've got an email question here from Karachi in Pakistan, Sunbul Hamid, and he wants to know, how can he attain his life goal of interning or volunteering for NASA?
You know, it's important, I think, no matter what country you're in, to look at opportunities, first of all, inside your own country, because all those countries, believe it or not, most countries of the world do have space programs of some type where people are building instruments or they're using NASA data to study that country to help solve the problems of that country. Remember, all that NASA data that we collect of countries from all all around the world. That's available for you in any country of the world to use, to study, to try to help your country. So I always encourage kids, first of all, to really think about the space agency or the technical agencies and companies, because you might be surprised how much your own country is actually involved in the space program. We do have internship opportunities. You can usually find out about them either through the U.S. consulate or embassy in your country, or by looking on NASA websites to try to find out about international student opportunities.
Okay. And that brings us to 8 o'clock, which means some kids are still going to go to school tomorrow. Yes. And become astronauts for the next day. So I would like you to please put your hands together and give Dr. Coleman and Dr. Stofan a warm round of applause. I know that they have agreed to stay just for a few minutes afterwards if you would like to ask them that burning question that you might have. So they'll be hanging around over here if you would like to come and speak to them. For those of you that would like to let your friends know if they missed this presentation, they can watch it on livingmaths.com. The YouTube video should be there. And thank you very much for coming out to the Science Center. Thank you for the US Consulate for making this very possible. So please, let's give them a round of applause. And we're going to end the broadcast over here. Bye-bye, everyone.
So.